Okay, we're going to go ahead and get started here. A couple things before I begin. First off, I'm not Mr. Freeze, okay? My real name is Jerry Zimmerman. I'm a physicist at Fermilab. Now, Fermilab's a national lab run by Department of Energy. We do a particular type of science called high-energy physics, particle physics. As I said, I'm a physicist there, and if you've ever seen The Big Bang Theory, okay, I'm more of the Leonard Hofstadter, Berkeley Sheldon Cooper type physicist. Well, except I don't ever really have girlfriends, so that's kind of a... So the area of science that I work in particular is called cryogenics. Now, kids, cryogenics is not the science of crying. So we know crying during demonstration. But it is the science of the extreme cold, thus my nickname, Mr. Freeze. Before I start horsing around, I always like to give you a chance to see what I'm working with. We sometimes refer to this stuff as liquid air, but technically it's only a portion of the air. This is liquid nitrogen. That's it. It's just a clear liquid. In fact, if you didn't know better, you could actually very easily mistake that stuff for water. Now, there's a few things that we notice right off the bat that do seem a little different. First of all, what's this stuff coming up here? Steam's hot. What's this stuff?
Nitrogen.
It's fog. It's water vapor. Just like you see your breath in winter. Same effect, only this is caused by the fact that the liquid in the bag is so cold that it's condensing the water vapor out of the air around us. What's happening to the liquid in the bag? Bubbling. It's bubbling because it's boiling. It's boiling because everything's so hot that everything makes it boil. My glove is so hot that liquid, so my glove makes that liquid boil. Just like electric iron make water boil, my glove makes that liquid boil. Well, here's where to help me out. If you want to know something, what do you have to do but ask a question? As I go through the show, I'm going to regularly go like this. What I want you to do is ask me the question, how cold is it? So let's give that a try.
How cold is it?
It's so cold, it makes a snowman shiver.
How cold is it?
It's so cold, it turns Smurfs blue.
How cold is it?
It's so cold, it thought the Arctic vortex was a heat wave. Okay. What you actually need to know the temperature of something is a thermometer, and I have a thermometer here, about 70 in here, very nice. But actually pour this liquid on my thermometer, and actually measure the temperature. So I pour this liquid right on my thermometer like that. So measure the temperature of the liquid is really at. So liquid nitrogen is about 45 degrees. No, what happened? I didn't break my thermometer. The thermometer's working just fine. What it's actually measuring is minus 320 degrees. That's how cold this liquid is in these containers. And because it is so cold, it has a very powerful effect on lots of things. Now, one of the first things that we noticed was that the liquid is boiling. Now, when you boil water, you get steam. This isn't water, this is nitrogen. So what am I going to get when I boil nitrogen? Nitrogen gas, or basically air. So I put a little bag, seal the bag up. What will happen is that bag will fill with nitrogen gas caused by the leak side, expanding and inflating that bag. See, it makes lots of gas. Oh. Okay. I guess this bag really wasn't big enough for this job, so I'm probably going to need a bigger bag here. Oh, actually, before I continue, I am going to need a little help with some math. So I'm going to give everybody a little mental math exercise. It's a very simple problem. Should be able to figure this out really easily. Now, I need to know how many seconds there are. Okay, seconds in a year. Seconds. It's really easy. It's 12. Yeah, January 2nd, February 2nd, March 2nd, April 2nd. I thought about those other seconds. No. I thought it's leap year and had a second for no good reason. Okay, so I got a bigger bag here. Now, one of the things I can be doing as I do this demonstration, a little scientific investigation. Now, investigation is what we call the expansion rate. So basically, how much gas do you get from a given amount of liquid? If I start with, say, 1 cup of liquid, how many cups of gas will you get? Well, the way to find out, of course, is you take 1 cup of liquid, you put it in your bag, you seal your bag up, and you'll see how many cups of gas you get for each 1 cup of liquid. Now, this is a good-sized bag. Got lots of cups of gas. Kind of use this table here as a hot plate, warming it up for me here. There we go. See the cooking in there. So what do you think? Is that bag going to be big enough so 1 cup of liquid convert to gas? No. So tell me, what do you do when you have a little scientific setback? Do you give up? Do you quit? No! You buy a bigger bag! So I have a bigger bag, and I repeat my experiment. Start with 1 cup of liquid again into the bag. Now, the good thing about this bag is that I know this bag is, in fact, a 45-gallon trash bag. This bag here holds 45 gallons. But wait a second. I don't need to know how many gallons of gas I get. I need to know how many cups, because I'm trying to make a ratio of cups to cups. So I guess I need to know how many cups are in 45 gallons. All right, first I need to know how many cups are in 1 gallon. So how many cups are in a gallon? 16 cups in a gallon. 45 gallons in the bag. Okay, 16 times 45, that's a little trickier. So is this bag going to be big enough? Well, 1 cup later, convert to gas. 16 times 45. Going once. You better hurry up. 16 times 45. Going twice. And the question, is this bag big enough? So 1 cup later, convert to gas. 16 times 45. And the answer is yes. In fact, this bag is just big enough. So 1 cup liter for gas from actual numbers. For each 1 cup liter nitrogen, you get 700 cups of gas. By the way, 16 times 45 is 720, so this bag is just big. Now that's fine, but the truth is that's not very convenient. It'd be much better if I actually, much better if I actually had a container I could hold it in. Now, because I am kind of the clumsy sort here, I have to make sure I put a cork on that so I don't spill any of it. Is there a problem? Oh! Okay, that's what happened. Okay. Actually, this is kind of a neat way to demonstrate another principle of science. Is that if I kind of turn things around a bit and do it this way. So, what principle of science was I trying to demonstrate there? Rocket propulsion. The reason why the bottle flies away, because it is just like a rocket and its cork comes off. But the truth is, that's still really not what we would do. What we'd really do is this. What happens in this case? The bottle blows up. Yeah, in fact, I know somebody in Fermi Lab, when they did this demonstration and the bottle blew up, it broke his nose. Good seats in front, right? I thought you said something about being really brave. And, by the way, it doesn't have some sort of nose radar. It could hit you anywhere. But wait a second. Why would somebody knowing the bottle's going to blow up be standing here holding it? See, one of the things about working in science is understanding how to handle things safely. So how do you prevent this bottle from blowing up? You poke a hole in. By the way, bazinga. At the end of the demonstration, it'll actually be detonating one of these bottles, so see how powerful it really is. It is quite dramatic. Okay, we investigated the gas expanding. Now we're going to investigate what happens when you introduce the gas into it. What's going to happen to a balloon? It's going to pop. It's going to freeze. What's the frozen balloon going to find out? What does it see in here? Oh, this is quite interesting. Yeah, it's going to change color. Oh, I'm sorry. No, it's going to change. No, that's not it. Okay, wait a second. There seems to be a problem here. Is that's okay? Wait a second. How about no? Okay, is that's not it. Is it no? How about no? That's not it. Is it this? Yeah. No. Okay. How about no? Is it no? What color is that balloon over there? Yellow. There. Oh, there it is. The air inside those balloons collapses that 700 times. Once you bring the balloons out, the air inside warms back up, re-expanding, re-inflating to the same shape size before it started. That's the reason why all these balloons are up inside the container. Oh, by the way, in sort of an odd timing thing, I recently got done working on an experiment at Fermi Lab, and this is the truth, okay? The name of that experiment is called the dark side. I was working for the dark side. It's actually a cryogenic detector in Italy. If you want to Google that, you need to Google Dark Side 50, otherwise you'll never find it in a million years. But when I was asked to join that experiment, I was told it was going to require some long hours, some weekends. And I said, okay, if I join your experiment, what do I get out of it? You know what they said? They said, give me a lightsaber. I was expecting something other than a very, very lightsaber. By the way, I don't think these are very dangerous. I know how big deal the movie is. You can't hurt anybody with this thing, right? By the way, this is good for something. Very good at making cold cuts. Oh, you do know what this is, right? It's a special type of puppy dog. No. It's a chili dog. Chili dog. Yeah. I was going to use this balloon here. Oh, it doesn't fit. Oh, wait a second. What if I help it along? As the air inside that balloon cools down, you'll collapse it. Remember from the movie right by now, she's saying, Dorothy, you wicked little girl. As the air inside that balloon cools down, it collapses in right there. What about a more rigid thing? There's an empty bottle. There's a regular cap. How about an even more rigid container? There's an empty can. I sealed the top with tape, so now basically it's just an aluminum balloon. Now, one of the things that's interesting about this, what happened to the balloon when I brought it back out? It reinflated, came back exact same shape and size. Helped plastic bottle on my hands here, warmed it up. Plastic bottle, there we go. Comes back. Aluminum can. Does not. There's a reason for that. Some materials are permanently affected by cold temperature. In this case, aluminum. The aluminum actually becomes a stronger material. It's actually called cryo treatment. Very standard machine industry nowadays to cryo treat different metals to make them stronger or whatever for certain applications. So if you ever see on that cryo treat on a product, that's basically what they did, is dipped in the nitrogen to make it stronger, whatever. You'll notice when I'm working up here, it does kind of look like I'm reaching in these containers, and I can actually see where the liquid inside container is. I have different things for different jobs. I had these blue gloves. These are special cryo handling gloves designed to handle extremely cold things. I have the tongs. Very good for like getting balloons in and out of the nitrogen here. But you think the hazard of this stuff is that you wouldn't want it to get on your skin. So you'd wear some type of protective gear to protect your skin from contact. Now this black glove, from that this is a special glove, it's been guaranteed tested liquid type. So no liquid can get through this glove onto my hand. So this goes perfectly for me, like, reach in, grab something. Is this a bad idea? Yes. I mean, what's going to happen? Like, fingers just going to bust off? No, I didn't actually lose anything. But this glove isn't very good at working in cryogenics because this glove itself changes into something that's, in fact, much more like glass. In fact, why do you think I'm wearing this white glove? Because of the cold temperatures? No. Because, why does that have glass? What would happen to my hand? I cut my hand. Do you know how hard it is to explain to people how you cut your hand on a rubber glove? Show me. But what would really happen if I put my hand in there? If I put my hand in there for a few seconds, I would get on my hand what is called a cryo burn. Very similar to a fire burn, same body physiology going on. In fact, a few minutes later, all the skin would peel off my hand. Because it burned the skin off the hand, same way starting a fire. Actually, my hand in there for about 5 minutes, it would freeze solid. Now, let's get rid of those TV shows, movies, seeing you do not shatter like glass. That's not the way the body is. The bones stay about as strong as they are now. But having said that, what in the world do I be thinking of? Oh, man. Why can I not put my hand in the container there? I can hold my hand here. I can kind of demonstrate that with this. I have here, get it out of here, a track, a track, and I have it to demonstrate a property of material, or the fact of this. What happens when I pour this liquid on this track? The reason why that goes running across that track that way is the same reason why. Let me put my bag back over here. Okay. What happens when I pour it on the table here? It goes running off the far side of the table. The reason it's running across the table that way is the same reason why I can hold it in my hand. See, if I was using a different liquid, let's say I was using water, and poured water on my hand, what did my hand get? What did the floor get? It's not wet. The floor's not wet. So what happened here? That liquid did not touch the floor, did not touch my hand. My hand to floor is so hot that it's boiling before it reaches the surface, forming a gas. It's actually called the Lindenfrost or Leidenfrost effect, depending on who you talk to. And the surface of the thing is so hot that it's boiling for resources, forming an air gas burst in contact. See, the real hazard is not your skin. The real hazard is something that can actually absorb a liquid. This cloth is wet with nitrogen. That cloth against your skin, you transfer the cold temperature, giving you a burn. You ever go to a doctor and get a wart burned off? What these are the cotton swab with Q-tips to transfer that cold temperature to kill whatever you're trying to get rid of. Now, I quite often get asked, by the way, a little background information. Fermilab allows me a couple of days of my work schedule to go to area schools to do this demonstration, to promote science in the classroom. That's the reason I'm Mr. Freeze. After hours weekends like this, I volunteer my time for. But I quite often get asked whenever I do a demonstration at a school, can I do that? And if you notice, okay, when I do this, I'm very careful not to toss it where I get on somebody else, or toss it where I get on myself. So the only way I can actually teach somebody how to handle ignition is what? Is if everybody in the area is naked. See, if you weren't wearing any clothing right now, this would be a perfectly safe demonstration, right? Oh, wait a second. There's something else on your body absorbs liquid in there. Air, yeah, see what happened to me? No, it's nothing to do with where you're in right now. This here is pretty neat stuff. This here is a 4-liter door, 4LD. Now, 4 liters is about, how much in U.S. terms? It's about a gallon of liquid nitrogen. So how much do you think a gallon of liquid nitrogen costs? Is it like, $5 a gallon? No. $10 a gallon?
Yeah.
20?
No.
Try $1 a gallon. In fact, in really large quantities, like we get a Fermilab, we get liquid nitrogen for 25 cents a gallon delivered. So why is it so cheap? First of all, where do we get it from? The air. All the nitrogen flowing around here is going in the air. You're breathing all in. Bees will kind of breathe all back out again. It's just recyclable. By the way, this is government nitrogen. I do have to take accounting for everything, so please keep track of all your breaths so I can keep track of how much nitrogen is going in and out here. Secondly, what do we really need out of the air? Oxygen. Liquid oxygen is much more valuable, much more commodity. Nitrogen is just a byproduct. That's a good thing it is so cheap. We do use a lot of it there from there. Ever seen those big trucks? Each one of those trucks holds 7,000 gallons. We use 2 of those trucks every day. But you know a company that uses more than we do. You've eaten their stuff frozen in liquid nitrogen. They probably should put a sign on the door right next to the clown's face. Yeah, Ronald McDonald used liquid nitrogen to freeze that hamburger you ate last week. Ever wonder why it looks the way it does? Now you know. That's all bad. Okay, first off, it's 25 cents a gallon. You freeze a lot of hamburger with 25 cents. Secondly, it's just nitrogen. You can dump a truckload of stuff directly on the food, and it will not affect the quality or safety of the food. And the third reason McDonald's Corporation does it, I can demonstrate this way. Put some water in this bag, and I'm going to add some liquid nitrogen. I was kind of doing a demonstration myself. I have in this bag 2 liquids. One liquid is boiling, while one liquid is freezing. One liquid is going from a liquid to a gas at the exact same. So which one is boiling? Nitrogen, that's right. Which one's freezing? What am I making? By the way, it's so cold it makes ice scream. Oh, that came out wrong. Wait, not screaming ice. We just turn around the other way. That works out okay. Now this ice I'm making here is regular standard water ice. Very odd shape to the way it was formed. It also has the property to get a little smaller pieces. This ice is so cold. This ice, there you go, freezes to my skin. It's so far below 32 that it freezes to me before I melt it. Same idea as you're talking to a flagpole in the winter. Don't do that. It really works. If you want proof, I'll show you the movie again. And again, and again. So whenever I try to eat that ice, freeze to my tongue, be pretty painful, yeah. So what in the world would I be thinking of with a marshmallow? Obviously don't have a campfire up here, so I have to use the next best thing, which is of course liquid nitrogen. So now the question is, what do you do with a very well frozen marshmallow? Now some people have suggested I make s'mores. The problem is s'mores are supposed to be mushy, and this is no longer mushy, it's now crunchy. So now the question is, what do you do with crunchy marshmallows? It's not make Lucky Charms. I'm really not sure what those things are, but actually, if you don't mind, I did not have a chance to have lunch, so if you don't mind, I just kind of have this as a snack. I'm sorry. I should not be smoking in front of you kids. Well, that was smoking, that was fogging. There's already a fog. But wait a minute. Why do they eat the marshmallow? One of the things about marshmallows that most people don't realize is marshmallows, in fact, extremely good insulators. What insulators do is they don't transfer temperature well. That's why you insulate your house. You don't want the hot or cold from outside to the inside. Well, marshmallows almost as good as the insulation you have in your house. Don't go home and insulate your house with marshmallows. What kind of land? But a marshmallow is such a good insulator, it will not transfer the cold temperature to me well. So even just as cold as the ice, I can take it out and eat it, and it will not give me a burn. Ice isn't near as good. Will transfer the cold temperature fast enough to give me a burn and be very painful. By the way, those that have seen the show before, I am sorry to say, but Friend Lab Safety has told me I no longer can offer marshmallows at the end of the show. I do not know why they consider it a safety hazard, but they have deemed it a safety hazard and no longer allow me to do that, so sorry. I quite often get asked, why in the world we use so much liquor nitrogen in the affirmative, and I demonstrate that a couple of ways. First off, I have here an electromagnetic coil, and there's a law called Lenz's law, L-E-N-Z, that anytime you put an electrical conductor, like this aluminum ring, into a changing magnetic field, it produces a current in that conductor, and that current makes it a magnetic field opposite to one's in. So when I activate the coil, now that's good, but we at Friend Lab just don't want good electrical conductor, we want great electrical. So how can we make this a better electrical conductor? By doing this. By cryogenically freezing it, it will become a better electrical conductor. Oh, by the way, it's so cold it gives goosebumps to a penguin. It's so cold every picture it takes is a freeze frame. It's so cold it gives, no, I forgot. It gives the frostbite to a polar bear. There we go. Okay. Now that my ring has been cooled down to cryogenic temperature, it now has become a better electrical conductor. And when I put it back into the same magnetic field as before, it will produce a higher current. And in this case, go much higher. The reason it's going higher is because it's producing a higher current, and therefore, by the way, if I let this warm up a little bit, will it go higher or lower? Lower. The more conductive, the warmer it is. So you actually use as sort of an odd thermometer how high up it is to determine what temperature it's actually, if you could actually catch it. What do you? Oh, here, don't let me get it. There. Okay. So that's good, but we at Friend Lab just don't want really good electrical conductors. We actually want perfect electrical conductors. I have here a special track, and this track is special in that this track is actually made of extremely powerful magnets, and I have it to demonstrate a property material. We use a lot of it at Friend Lab. And that property is what we call superconductivity. Now some materials, when they get extremely cold, become what we call superconductors. Now most of those actually operate at minus 450 degrees Fahrenheit. But a few very special ones, what we call high temperature, actually operate at minus 320. This can has some of that material in it. Right now, no magnetic properties at all. But once it gets cooled down to cryogenic temperatures, it will become a superconductor. And when you put a superconductor into a magnetic field, you get what is called the Meissner effect, related to Lenz's law. Oh, I almost forgot. It's so cold, it gives a slushy brain freeze. It's so cold, it gives you brain freeze just thinking about it. Yeah. So now that my little can has been cooled down to cryogenic temperature, it will become a superconductor. And when you put a superconductor in a magnetic field, you get what is called the Meissner effect. And in this case, what that means is that my little can here, once it gets fully cold, it's almost there. There you go. It will, a little bit better, come on, a little more, there. Float on that magnetic field. So this is a demonstration of magnetic levitation, the Meissner effect, and high temperature superconductors. As you see, it goes very easily because there's no resistance. The other thing that's kind of neat is not only does it work this way, but it also works this way. So not only rise that up, but upside down. So that's a demonstration of high temperature superconductor, the Meissner effect, and magnetic levitation. By the way, that also proves you can have a magnetic levitating train in Australia and it won't fall off, in case you're wondering. Hey there. So, okay. Any questions real quick before I guys more damage and destruction up here? Is it great or terrible? I'm not sure. Okay. Next thing. Oh. Yeah, yeah.
Next.
Oh, yeah, oh, yeah.
What is the example if you freeze mercury?
You can freeze mercury with it. The only problem is mercury is considered such a hazardous material. Nobody in their right mind would let you ever take mercury out of a container and touch it and freeze it. So you can't actually do that demonstration because they consider it a safety hazard because mercury is such a dangerous material. But yes, you can actually freeze mercury. You can make it solid. It actually turns solid at minus 86 degrees, so it's quite a bit warmer than where this is, and therefore freezes solid.
Is it possible to like freeze like soda or pop?
Yeah, you can still freeze. You can put soda and pop in your freezer and freeze it, and you'll end up with a really big mess at the same time. By the way, we may get to that point in just a little bit here, so we'll talk about that. So, any other questions?
What's your favorite atom on the periodic table?
Ooh, favorite atom. That's a tough. I kind of like helium just because it doesn't have a solid phase, so you never can really, But that's a tough one. Yeah, I should have like nitrogen just because I do these shows, but that's kind of a, 7, who cares type thing.
Do you freeze a bottle and like smash it with a hammer?
Freeze a bottle? What type of bottle? Plastic bottles? Plastic bottles don't actually change much. They actually survive the cryogenic temperature just fine. They really don't change mechanically or physically very much. Other materials do change dramatically. They actually become very brittle or whatever. So that you can do. But the plastic of the bottles is virtually ineffective.
Why doesn't alcohol freeze?
What?
Why doesn't alcohol freeze?
Alcohol will freeze.
Okay.
You get it this cold and it freezes. And it's kind of neat. You can actually make alcoholic ice cubes. It's kind of interesting. And then what you do is you take the alcoholic ice cube and put it in your drink, and as it melts, it makes your drink stronger, not less strong. So it's kind of a bad thing as it works out, but you actually can make it. You can actually do it the other way. Yeah. Right, certain metals change because of the cold temperature. It's actually called cryotreatment. But yes, this aluminum is stronger than it was before. So it takes more air to force it back out into its original shape because it is stronger. Oh yeah, there's lots of materials that get cryo-treated all the time. Lots of steels, lots of metals do become better in some aspects when you cryogenically treat them. The machine industry uses it for cutting tools because the cutting tool wear price is much higher after being cryo-treated. So yeah, there's lots of materials that do change that way permanently. So okay. Let's go ahead and continue. Okay. What? Food? All foods will freeze. At this temperature, absolutely everything pretty much freezes at this temperature. I mean, there's only a few things that do not actually freeze at this temperature. And certain foods are more interesting frozen than others. I'll give you an example here. This is one of those demonstrations that I don't often do, and the reason is because I just don't consider it a very practical demonstration. But it is the banana demonstration. Now, it's pretty straightforward. You take a normal, everyday banana. Now, some people actually cheat and they don't peel the banana first, but actually the inside of the banana is softer than the outside of the banana. Secondly, I was told I need to prove to you it's banana. I don't know why, but that's because I'm hungry. That's because I'm proving it's a banana. Now, what I am making here is a frozen banana, and yes, you can buy a frozen banana at the store. It isn't like the ones at the store. It doesn't have any chocolate or nuts on it, so that's one strike against it. Secondly, even though it is technically safe to eat, I mean it's not chemically changed because of the cold temperatures, it's not very safe to eat in another aspect. And I almost forgot here, wait a second. It's so cold, let's see here, I forgot what I was thinking of. Yeah, got a good joke here. Put it in there. Yeah. Okay, now a banana has been frozen. You can actually take a banana out. Now this is the reason I don't consider this a very practical idea, is that, see now, this is much better to be used as, say, a hammer. And I don't think many carpenters are out there going to be building houses with frozen bananas, so that's kind of a... Now, the reason, like I said, I don't consider it very practical is I don't think this is a good tool in the industry. But there is something I came up with that's kind of along the same lines, and it's related to something that happened in history a little bit ago. How many of you remember hearing about the Space Shuttle Challenger disaster? Space Shuttle Challenger exploded shortly after launch, killing all 7 astronauts on board. Ever wonder why? Right there in my hand is exactly the reason why. This is a Viton O-ring. This Viton material is extremely strong. You and me are not strong enough to pull apart. It's a very flexible material. Stays flexible down to minus 40 degrees Fahrenheit. Did you ever get to minus 40 degrees Fahrenheit in Florida where they launched the shuttle? Oh, so what happened there? Well, right next to the rocket engine that has this Viton O-ring in it, there's a large cryogenic tank of oxygen and hydrogen used for rocket fuel. And on a very cold winter morning, that O-ring got cold enough that it changed from its flexible nature to something that's in fact much more brittle. The O-ring snapped on launch, causing the gas to escape, caused the explosion to kill the astronauts. We call this our Fermi snake, eventually worn over in a line course there. But I said, that's such a strong material. What if I took a smaller piece of that material, which I have here, and now, in a bit of a reversal of fortune, we'll take my piece of Viton, and now, the reason I think this is a far better idea than the banana hammer is that when the banana hammer warms up, what I have is banana mush. When this Viton, piece of Viton warms up, and I'm going to help along my hands, like my Fermi snake is starting to do there, this piece of Viton will in fact regain its flexible nature. So now I have invented the rubber nail. I just cannot figure out what I'm going to build with rubber nails. I don't want my house doing that. Seems like a bad idea. Somebody had suggested, how about building a house in an earthquake zone? That works really well, of course, till the wind blows and your house flips over sideways. That's really bad. Now, we in the Midwest or Texas could have fun with this idea, of course, if our house happened to get by a tornado. We could ride the storm out. By the way, with my one patent of life, I'll stick it out for that someday, so I'm get a thousand wealthy anytime soon, that's for sure. Okay, next one. We're going to do a little experiment. I'm going to do a little background demonstration first. Give me my Fermi snake back here. I have here, a racquetball. These guys around. A racquetball, a tennis ball. You can actually hear something quite unique in this setting if you listen carefully. Racquetball. Not that much. Tennis ball. That popping down you heard was actually thunder. Thunder. How could that be thunder? What thunder is a sonic boom caused by air expanding faster at the speed of sound. In case of a lightning bolt, is the heat of the lightning bolt caused the air to expand so fast. In this case, the cloth coming in the tennis ball caused the nitrogen to expand so fast. Same thing here. Tarp, not much. Carpeting. That sound is in fact thunder caused by the nitrogen, the carpeting making the nitrogen expand so fast. Now I do this kind of a background demonstration, which is kind of interesting by itself. You ever wonder why certain sports don't catch on really big in certain parts of the world? This is a good example. Racquetball in Alaska, not a good idea. Hit by that, you're probably going to be sorry. The Alaska Open, not one of those big tour events on the old tennis circuit out there anytime soon. Get hit by that tennis ball. Actually, in Alaska, they do not call it tennis. You know what they call it? Dodgeball. Hit by that ball, you're out. You're going to doctor hospital. So with that, I do that. I have a background demonstration. And whenever you're doing a science experiment, what you're actually trying to do is answer a question. So in our case, our question is, what do we think, let's put him back, what do we think is going to happen to this ball? Now before you do your experiment, you come up with your hypothesis, your educated guess. In our case, we could look at similar examples. We did a balloon. What happened to the balloon? Collapsed and came back. We did a racquetball tennis ball. What happened to them? It got hard. What's going to happen to this? It's going to collapse like the balloon. It'll get hard like racquetball tennis ball. How many say it's going to collapse like the balloon? How many say it's going to get hard like racquetball tennis ball? How many are not voting in this election? So we'll do our experiment. Now the reason why the balloon collapsed is the air inside the balloon collapsed. Does this ball have air inside of it? Yes, it does. Oh, it didn't collapse. It got hard like a racquetball tennis ball. Okay. But what happened to the air inside that ball? Does it still collapse? Yes, it did. It had to because it got cold. It had to collapse. So now I have a hard brittle exterior with a collapsed gas or a vacuum inside. What does that make this like? No, I'm not voting. I'm pointing to a light bulb. Tell me what happens to light bulbs when you hit them? They explode. The reason why that ball explodes that way because it is just like a light bulb. You hit it and it blows into 1,000 pieces all over the place, just like a light bulb explodes. Okay. Okay. This next one. This next one is for you ladies. No, I'm not giving you flowers. But you ladies should know the connection between flowers and cryogenics, and it's something about flowers as well. They smell nice. And if you want to smell pretty as a flower, you take flower base and rub it on your cheek, give you rosy red cheeks. We started with rose, right? But wait a second. Where do you get that pretty flowery smell? Perfume. How do you get that pretty flowery smell into the perfume? They do it this way. By cryogenically freezing the flower. All the fragrance gets locked in the petals. Then the flowers can be taken out. The petals can be crushed. And the fragrance processed into perfume. Those flower-based perfumes use cryogenics to process the fragrance out of petals. Oh, by the way, it's as cold as the heart of a guy that would do that to a flower. Oh, that's right. I'm sorry. Okay. Okay, I think you're ready for this. Actually, if you don't mind, I'm a little thirsty. If you don't mind, I'm going to have a drink of my pop here. Oh, you know what? My pop's warm. I don't like warm pop. Oh, wait a second. Oh, I got this. See, you know what I can do? I can take and put some of my liquid nitrogen stuff right in my little thermos here. And then I will take my pop, put the cap on. In just a couple of seconds, I will have, this will be great, because it's only going to take a couple of seconds for that to get nice. This will be, so it's great. So, the good news, my pop's cold. Oh, but now it's flat. I don't like flat pop either. By the way, if you're wondering what happened, at the point the pop reaches its freezing point, all the carbonation comes out of the liquid, causing it to come squirting out of the bottle that way. Hey, wait a second. Is that the reason why they call them fountain drinks? Everything is fountain. Okay. Let me explain what's going to happen here and what happened to that poor guy in front of them, I know. Basically what he did is he took one of these little plastic bottles, he put some of their nitrogen in it, put the cap on it, threw it in a trash can, stepped back, waited for it to go off. And he waited, said, I must have done something wrong. So I looked at the trash can and see what's going on. That's when the bottle went off, hit him in the face, broke his nose. What he did not realize is A, how long it takes to do, and B, how powerful it is. Without any help, this bottle takes 3 minutes to develop enough pressure. When it goes off, it has over 250 psi pressure. That's what this bottle is designed to withstand. When I try to figure out how to do this demonstration for schools, I can't wait 3 minutes to see the bottle's going to go off. So to come with a solution to this 3-minute problem. The solution to this 3-minute problem is actually pretty straightforward, and I actually already showed you. What can I add to this bottle to make the nitrogen boil faster? Water. As you saw the Ziploc bag, this now makes the nitrogen boil so much faster. Then now this bottle will take about 15 seconds. Now 15 seconds, I have enough time to put it in the can and step back, but it isn't so long when it's actually going to go off. Now a few things I need to advise you. First of all, that 15 seconds is only an approximation. I cannot count down 5, 4, 3, 2, 1, have it go off. I mean, these bottles aren't manufactured in a huge low precision. Secondly, when it goes off, it is extremely loud. So if yours are sensitive to loud noises, you want to put your hands over it. It's safely loud, but it is extremely loud. So, I need to be absolutely positive about just one thing, and that is, are you ready? Yeah! Now that 15 seconds doesn't start until after I put the cap on the bottle, that's when pressure starts building. So until that time, there is no hurry. It's not until I do this, Now I have 15 seconds, and I cannot stop it.
I'm going to die.
Too late now. You have one on your eyelash. This,
Oh my god.
yeah, that's, yeah, well. Sometimes, you know, it doesn't quite work out. Maybe after the next show, come back out. I don't know. This is all that's left of that poor bottle that gave his life for this demonstration. As you see, it's right about that. A couple things before I continue. I do have a Facebook fan page, website. There's some neat slow motion videos, different parts to show up there, so check it out. I have a blue flyer there. Feel free to take one. Some fun information about cryogenics to me and all that, so check that out. But now, kids, I always like to be sure that whenever I do one of these demonstrations, do you get to leave this little demonstration with something, and it's not a confetti shower like we just got. What you're going to get to leave this little demonstration with is a little science homework assignment. Actually, kids, I would almost be willing to bet you that you'd have a hard time not doing this homework assignment. See, our homework assignment has to do with where I work, Fermilab. Fermilab's claim to fame is that we have some of the world's most powerful particle accelerators. We actually have one that shoots the particles right through the earth to Minnesota. So, how many of you have a particle accelerator at home? I have 5 in my house. I'm at one. So now the question is, what do you think you have in your house as a particle accelerator? Any idea? Okay, I'll make it easy on you. You watch it every day. Your TV set, your cathode is an electron gun. So your homework assignment, kids, is to do what we do there at Fermilab, and it's not watch TV, okay? It's to go home and operate your particle accelerator. You can handle that one, right? That's not a problem, right? Well, I hope you enjoyed the show, and I hope you learned a little something along the way, so thank you. You can exit out the left. No, it's all part of my glove. Oh, thank you. I don't know what I'm supposed to use it for. I think it's kind of close.